Hey everybody, this is Larry. This is day 21st of the Leetcode Day Challenge. Yeah, hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Median of two sorted arrays. This is a classic problem. Um, just, I mean, it's even so old that it's as a four. I think probably when it came out or when Leetcode started, it's probably a reasonable hard, but I think it'll be hard to imagine people would call it a hard these days. All right, so we're trying to find the median of two arrays. Of course, if you just you know combine them and sort, then that is going to be way too long. That's already uh, you know m plus n log m plus m or something like this, right? And you're trying to get this in log of m plus n time. So yeah, I mean, I think. Mm, hmm. I think the key part about solving these problems in general, and I talk about it a lot, is about figure out the invariant, right? As you kind of change different things. In this case, you're trying to do sublinear, right? So you don't even have time to kind of look at one element at a time. Well, it's a little bit clunky that we have to get two elements, but I mean, I don't know why they. I would just find that amusing that they used to be like pretty good about constraints that they give you this as a constraint, even though this kind of implies that. Though I guess the one kind of technically makes a little bit of a different detail, but it's okay. Right. Um. So, what would be something that we can do, right? Um. Hmm. I mean, my first idea, to be honest, is just binary search for the answer. Uh, and because sorry, I'm outside, it's like playing some music. Because the arrays are sorted, we can do log, let's say R for the range of the numbers, right? So log R number of iterations, and each iteration will only take uh, um, log M time or something, right? Or each iteration we have to do two binary search and then log m plus log n, and then just do some math and then keep on going. That of course does add in a log r factor, so that's already kind of too slow. Um, I actually don't remember this one, even though I said it was classic. Uh, I think one thing that I would kind of be tempted to do is just I feel like this is one of those trick problems in which I don't remember the answer. But because at that point, to be frank, log r times log m plus n, or log yeah, log m plus log n, it's going to be fast enough, right? Like the log r factor is just I guess technically that adds uh, like a 20 multiple or something, but still, given these small numbers, it should be good. But let's step back for let's step back for a second, right? So what we probably want to do is some sort of divide and conquer, and what's the median of one sorted array, right? Well, that's O of one. So I wonder if we can figure that out from like is that something that we can make an observation on? Um, like the median of the first array, and then just try to look at the other one, maybe. To be honest, not quite sure. Dun, dun, dun. And of course, you still have to be a little bit careful about this case, I suppose. I do wonder if you, I mean, my idea right now is just like figuring out, okay, so you're starting from the median of both arrays, and then kind of just like, you know, do some math on that. But I mean, I think that works. I guess it doesn't even. I mean, I think, okay, so let me walk back a little bit. So the binary search for the answer one, the lazy one, where we just binary search for the answer, and then kind of just get that. I think that, I mean, obviously that works, but that gives us an extra log R factor. I think maybe we can be a little bit smarter about it, because we don't need to fit the range of the numbers, right? We can maybe binary search on something like M and N, and then do it. But that does that make it better enough? Let's say we're given a number, right? And then we could do two binary search, one on the M array and one on the N array. And then that gives us a number. And then now we're trying to basically I want to say like then you would know, right? Because then let's say you just do a guess and then you could linearly walk. Of course, that in the worst case it's going to be linear, so you know that's not going to be Gucci. But then can we be a little bit smarter about, instead of linearly walking, we can do a binary search on that, on like repeated doubling or something. The actual implementation may be a little bit tricky, but I think technically maybe that would work, right? Yeah, I mean, I guess that works, but but actually implementing it, I don't know that is easy. Let's think about it for a second then, right? Let's say we took the median of the first array and took the median of the second array. What does that mean? So there are only four possibilities, right? And two of them are symmetric at least, right? So basically now you have some, let's say they don't overlap at all. They don't overlap at all and you took the median, then by definition, well, that's not true. I was gonna say by definition you take half of the combined array. I guess that always actually is true, right? Because by definition the median is in the middle half, so then we get rid of the smaller halves, right? ASCII or what? And then what? And then maybe we can do it again, right? And then yeah, I mean here maybe we can even just do a quick, you know, check on here, but in theory, like something like that, right? Even if we don't do a shortcut. And then another example would be something like this, where the overlaps are something like this, right? And then maybe you have a median here and a median here, right? I guess there's another case where actually it's something like this, where, but that's even easier, right? Like if you have a longer thing, and let's say they're not symmetric, right? And then the median would be here, and the median's here. Then you know that it is going to be in between these numbers. So then you throw away this one and this one, which is also by definition half, right? Of the things even then. And here in this case, you know that the median is going to be here. So then we remove this, and then we remove this, and then we kind of treat it as, you know, right? I guess that works. That should work, right? And now we don't have a log off factor. It's just that, yeah. I don't know if I could come up with. I mean, I think that works, but also worry about even number stuff. But we'll worry about the special cases once we get the core case right, I suppose. Right. So okay, let n is equal to nums 1, m is equal to length of nums 2. I think technically this is the opposite from what they showed, but I like it this way. Whatever. Let's just use n1, n2. Maybe that's actually more descriptive and less confusing. Man, I do not remember how to prove these from first principles. I mean, I'm trying to prove everything from first principles. That's what I'm doing. Okay, right. So how do we know we're done? Try to start everyone from scratch. Okay, so let's say we remove this, right? And then next we kind of look at this middle. Okay, I mean, I think that makes sense. And in theory, it can even, it looks here. So then next we know that it has to be here and so forth, right? Because basically, the median is the number that has the same number, same number smaller and bigger than it, minus the even case for now, right? So okay. Okay. Man, I can't believe I'm grinding for this. Maybe it is hard after. Well, it definitely is hard if you haven't done it before. So, and I don't think I've done it in a long time. This doesn't really come up in competitive. Okay. I don't remember any tricks for this one. I think the idea is right? Because you're basically trying to find a sort of a weighted median before this, right? So that this plus this, some line such that the left of it plus this is equal to the right of it plus right of it. Okay. All right. And that is. I think the idea is right, but that is just hard to write, right? That's hard to code. I'm trying to think whether, to be honest, I'm trying to be a little bit lazy and trying to think whether there's a cleaner solution, but maybe not. So let's just define the bounds then. Left, right is equal to 0. Right 1 is equal to n1 minus 1, right? Yeah. And then left 2 is equal to 0, right 2 is equal to n2 minus 1. And then now, okay, so the middle, okay, so you have two medians, right? And basically we want ideally, we kind of merge toward the middle. Is that always true? Oh. Man, I don't have basics down. This is how I struggle in contests. We'll eventually get it, but the basic is a little bit weak. I'm trying to prove to myself that that's true. I guess that's fine, because what that means is that okay, I'm trying to use this visualization a little bit as well. So if it looks like this, then the median, well, we know that the median cannot be here. and we know that the median cannot be here, right? If that's the case, because, and then we could do a binary search on that. Yeah, okay, fine. So, all right, let's do the while true thing for now. Mid 1 is equal to left 1 plus 1. Right, if have to do 2. I'm just like, I mean, it's actually not that hard to write, but I'm just like really worried about a lot of edge cases, which is why I make it harder to write. Or I think it's harder to write than from experience, I know it's hard to write, which is why I'm scared about it. Or like with respect to the number of edge cases, right? So it's to the right. What does this mean, right? And this is not that. This is nums. If this is the case, then you basically have this case, and then then now left 1 is equal to mid 1, right 2 is equal to mid 2, right? We'll just keep it inclusive for now. Else if nums 1 of mid 1 is greater than nums. Like I said, I'm not really confident about off by 1, so this may go infinite as well. So this may be a little bit sad actually, but what am I doing? So okay, so now is the other case. Then just for visualization for me, this is that. Then now we want to cut off the right one, so and then note that this is very infinityable, so that's why I'm a little bit worried. Otherwise, if they're the same, then technically I guess we can return nums 1 or something, but it's not good. Okay, so maybe while nums 1 that mid 1 is, but that would never be true for some of these, so right, like this one is just, well, they don't have enough numbers, right? So, and actually I always like it to keep it inclusive bounds, but I think we need to actually go out of bounds here to represent the before and after. Maybe I'll have to work that in. What would that actually look like? So then now I think the idea is fine, but I'm trying to visualize what it iterate to. And this is kind of hard too, right? Because okay, so let's say we draw it out for the examples, right? So now we have the edge cases is what I am struggling a lot with. So then here, well, this mid is going to be 0 and 1 over 2. So this is going to be, mid is actually going to be 1. It scales to, or it rounds off to the left. So then that's 1, right? The bound's going to be 1, and then the bottom is the bound's going to be if things the median is going to be 2. So then now the 2 is bigger than 1. So then now we make left 1 is equal to mid 1, which is exactly the same as this number. So that means this is going to infinite loop immediately. Because left 1 is equal to left 1. Is there a cleaner way to write this? I'm not gonna lie, during the contest I would have just used the log R thing. But or Unix, yeah, I don't know. I think this idea is right, but I don't quite know exactly how it's gonna, because usually in a binary search, the way that you would say it is that given this condition, what is not possible, right? And I'm a little bit lazy in defining that mid 1 is still possible. which it is in like a edge case kind of sense, but especially for like something like this where the median is actually not even in it, right? With even numbers. I don't know. I think I'm gonna cheat on this one. I don't know how. I think this is the right idea, but I don't quite know how to program it implementation wise, to be honest. So I'm just going to use the log R method, and then we'll review the implementation together. It's something that I just have to learn a little bit. I think one thing that I would say is that for those of you, the few of you, I don't know how many viewers I have left up to this 20-minute video, but I mean, we're all here to learn, and I think one thing I would like to kind of have these streams sometimes is, or recording sometimes, is that I don't actually know everything. I try very hard, and I know a lot just from being old, but and I'm always looking for ways to improve as well, given the time constraints that I have in general. So yeah, so let's use the log R1, right? And then see if, but basically the idea is that, okay, we make a guess, right? Right, so left could be -10 to the 6 or something like this. Or we can even just take the minimum element, right? Let's do that. So min, and the smallest element is, because it's sorted, it's just going to be one of these, and then the biggest element is of course also one of these, right? And then now, and this is just standard binary search now, right? So if I want to say good, but good is maybe yeah, let's just say good. I mean, I think you have to be a little bit precise about what good means sometimes. And good for a target means that is the number on the left half inclusive of the range, right? Or not, it doesn't have to be from the range. It has to be in the left half inclusive, and that should be good from 0 to mid, right? So that means another way to phrase it would be that it has that it is bigger than exactly n or n over 2 elements, and if it's odd, then yeah, n over 2 round up elements. So right, so okay, so then now we can do num1 index is equal to bisect left. Do we want bisect left or bisect right? Let's actually, I think we want bisect right to get the number of numbers we strictly bigger than, right? So n1 bigger, maybe larger. Larger sounds better. English is hard. I never know if it's larger or bigger. Sometimes, right? Are they unique? I guess they don't say actually. If they don't say, then we have to take account uniqueness and also possible rounding errors. What does that mean? Okay, so we have to change it a little bit actually. Let me think about this. So basically now we want the biggest number that wait, do we? The median, and that's actually a little bit not true either, right? Because the number's never going to appear in this for an odd number, right? But we can do the math on that one. We can just do the next number that's it's awkward, but I guess we can do it. All right, so then in that case, we want this. We want the biggest number that has less than n over 2 round up numbers smaller than it, something like this, right? So do I still want bisect left or bisect right? No, we want bisect left. So we want strictly bigger than. Okay, fine. But then now we're actually I lied about this, did I? No, maybe not. Maybe that's fine actually. I was debating whether it makes more sense to use and actually this is technically this is smaller. This is how many numbers this number is larger than, so the number of variables. So then it's like return smaller is I guess we have to do like n1 is 0. And then our target would be was it median is going to be you go to what how am I so bad at math? Something like this, right? Something like that, right? So we want the smallest number where this is true, I think, right? So that means that if this is true, then we want a smaller number. Otherwise, we try a bigger number. I don't think this is it. Wow, man, I didn't expect this to be that hard or annoying anyway. Right? I'm just running real quick. Oh, I forgot to put in the actual array. Nums1 and then target. I missed the other thing, not the actual array. What is 1 here? Right. 1 is the number. Is that right? Alright, this feels very awkward. So what is m? M, and left is, this should be the number, okay, right? So m, we want to find indexed 1 number, okay. Why is that returning 1? So 0 is going to be too small. This is 0. And then 1. Oh, this is just choosing 1 and 3. So this is 1 and 3. And then this goes, yeah, this is 1 and 3. So the mid is 2. 2 is going to be bigger than 1 number. So the bisect left of 2 is going to be on 0 and 1. So this includes 1. 1 is so we try something smaller. I think this is actually roughly maybe I'm off by 1 actually, but well, this is just awkward, so maybe not. Maybe I'm off by a little bit more. All right, let's take a look. Yeah. This one's fine. Okay. So we try the number 2 as a target. 1 number small. Oh, I see. Maybe we do need bisect right, bisect left. I'm thinking too much about the equal number case, but yeah, okay. So we need, in this case now we have 3 numbers. We want to find a number that is bigger than 1 number, right? Exactly. But somehow we get 3. That doesn't feel so right. 2. The 2 is so it's given 2, so it's 2 or bigger or smaller. That's what this is saying. No, I think I like bisect left more. I think I got confused. Okay. And just not include the number. Because then now we want the number that is bigger than technically 2, so I think I just need to adjust this by for odd numbers. Okay, so then now it's looking for 2, 1 and 0. 1 and did I have the signs wrong? If this is good, it's on the left side. Now, because if we have a lot more smaller numbers, no, it's only on the, I got confused. It's smaller numbers if we have more on the left side, so it should be this. Okay. All right. Let's see. And I think Leetcode 2 would be on the left side, so okay. All right, so given 2, we have 1 and 0, so we have to try a bigger number because 2 is only bigger than one number, and we want it to be bigger than 2, bigger than or equal to. I think we want this, but now we want bisect, right? Okay, fine. Man, I thought this one would be easier, but it's still a little bit wild. I think this is fine now. I think this is what we're saying, but we don't take care of even holds because now we're trying to be bigger than 2 numbers or 2 numbers or equal to, which is what we have done, which is the number 2, right? Yeah, maybe I'm a little bit lazy. I think I can do something like find right, something like this, right? And then now we can say if n1 plus n2 is odd, then we can just return find of m. If it's odd, we want, yeah, that feels right. So I would just put it here instead of. If it's even, then we will do the thing, right? Of if it's even, then we do this, and also this, right? And then we take the average of them, right? Oh, I guess this is oh, whoops. Okay, but I'm not confident about this at all, to be frank. It just feels a little sloppy. The actual code is pretty tight, but I'm always worried about, as you kind of saw, like I worry about this function in general, or even like a case where we have, I don't know, like a lot of ones, right, or something like this. Just like that. And also I forget that, yeah, this would actually give us our index. That's annoying. That's annoying. This is just annoying to write, that's all. I don't know why they don't make it at least one element, but fine. Okay, this is so silly. Oh. Let me know if there's an easy way to write this. There probably is. I don't know. But, okay. Yeah, I guess I can just do. And I could also just use have used the big numbers instead. But oh, I guess that works. I don't know. I'm still not that confident, to be frank. Like, I wouldn't be surprised if these kind of failed. But all right, let's just give it a YOLO submit. Oh, I guess that did work. 1269-day streak. Didn't C++. It's been like 4 years too. Wow, time really flies. Pre-pandemic. What did I do? I guess I did use the binary search. I guess I did it basically the same way that I did it today, but probably much quicker. But what is the intended solution though? I'm trying to think. I guess we do know the intended solution. I just okay, there's too much stuff. I don't know what's going on here. But okay, fine. I guess this is kind of what I was going for, but maybe not. I don't know. Let's see. Let's see if there's another one. Oh, I guess I could just click on editorial. Maybe that helps. Merge sort. Wait, what? Oh, I see. I mean, that's basically what I was doing, but I didn't have this terminology. I was just worried about like getting it. But I think maybe if I had this visualization, I could have maybe done it. But oh wait, no, not this. Well, not quite like this anyway. I think this is the thing that this is such a weird owl. But I think this one was what I was trying to do, but I don't know, just very easy to get wrong. And looking at this code, I guess it's kind of true, to be frank. Like there's just so many cases, you know. I guess I had the idea, but not that. And then I didn't even. I guess I did figure this out a little bit better after that. But in the same way that we could have just done this, but I don't know, a better binary search. I don't know. I think these are all fine ideas, but like yeah, I don't think I struggled with the idea per se, but I don't know that I can implement this flawlessly, easily. This is just so many if statements. I don't know. That's all I have for today. Let me know what you think. Let me know how much you struggle, because I really did. Yeah, stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.